Hello, my name is Moriah Hughes. I'm presenting on the structural investigation for preservation of Cuba's historic School of Ballet domes. I want to acknowledge my co-author, Camille Heubner, and contributor Sofia Celli, as well as our project and research advisors. The 5 schools of the University of Arts of Cuba, constructed just after the Cuban Revolution, have been well studied architecturally since their rediscovery and launch to international fame in 1999. But their road to recovery and preservation has been long. Environmental mechanisms and years of disuse have caused decay, particularly to the ballet schools. This and the cultural value has motivated the current study of these structures. Also, a more detailed site and archival studies were enabled by a grant from the Garatti Foundation in 2018 to fund preservation planning for the ISA campus. This new data has enabled, in turn, these more detailed structural studies. They aim to diagnose the structures, discuss the structural efficiency, and provide intervention recommendations for the preservation plan. There are 3 parts to the investigation. First, data gathering, including on-site and archival research, the creation of the structural analysis model, and lastly, the nonlinear finite element analysis. The archival research led by Sofia Celli and Davide del Curto helped reveal the construction methodology and section properties. The vaults employ a composite tile and reinforced concrete cross-section, some details of which are shown here for the large theater dome and then for the smaller classroom domes here. The survey and material data were provided by project partners, some of whom are shown here and to which we're deeply grateful. We inspected the theater dome, which has a 30-meter span, and no significant structural concerns arose during this. The dome has some limited efflorescence at the base of the ridge and some other crack indications at the ring beam mid-span, and then where the ring beam frames into the supporting pillars. But again, these seems to be normal lifetime reactions and not significant concerns. For the classroom inspection, these are a more unique and daring form, and this is seen in the damage evidenced. Within the arched edges, there's cracking from the 3rd points upward, and you can see some corrosion and spalling at the apex. The pendentive's extradose has numerous tile and, where visible on the right, concrete cracks. We made crack maps to compare the condition of the pendentives to each other, and these indicate that even where not visible, there are 2 or more major tensile cracks in the concrete section at the interior of the pendentives. This discovery is concerning and adds urgency to the structural analysis. We created the finite element model using a homogeneous symmetric solids model and embedded steel reinforcing, the red shown on the left figure. For the nonlinear constitutive model, a concrete damage plasticity was adopted and implemented in Abacus Explicit. Applied loads included dead, live roof load, wind, and settlement. For the theater, the finite element results show that the upper spherical dome is primarily in compression, as expected. Slight tensile damage exists for all cases at the rib base, but is not significant enough to cause concern. There's also some slight bending-induced cracking in the ring beam under differential settlement. Consequently, the FE results corroborate the observed damage, that there's no significant structural concerns for the choreography theater at this time. But we do recommend monitoring the efflorescence progression at the ribs and the shear cracking development in the pillars to see if the damage accelerates due to any causes and should be addressed at a future time. We also recommend avoiding differential settlement or disturbance of the pillars, as that's the highest demand that was analyzed. For the classroom, the FE results show that there's a high bending demand throughout the dome, primarily at the base of the pendentives, at the mid-height, and then at the apex of the arch, seen there. Also, it revealed that there's insufficient tension stiffening in the pendentives, as the rebar is shown in compression here at the same location of maximum tension stress in the pendentive extradose. The damage in the classroom can be summarized in 4 major stages up to collapse. First, tensile cracking occurs at the arch apex and pendentive base. And then the pendentive horizontal bending cracks occur on the extradose face. Thirdly, flattening cracks occur within the arched region, particularly the upper third, shown here. And then fourthly, the dome collapses when the hinges become fully plastic. And by hinges, I'm indicating the yellow areas shown here. And you can understand the collapse of the dome most clearly by comparing it to that of an arch. If the arched opening is an arch, then once these 5 hinges become fully plastic, a mechanism is completed. We validated the model by comparing the pendentive crack maps to the model stress and tensile damage, and you can see the good correlation evident there. In lieu of conclusions, the diagnosis of the classroom domes is not encouraging. The domes evidence damage stages 1 through 3, which is the 5 hinges initiation and the flattening cracks as well. This means their current status is that of undergoing hinge development, and we don't know how much capacity remains at the critical sections until they become fully plastic. Therefore, the pendentive capacity is insufficient for the bending demand, particularly due to creep, we believe, due to the insufficient tension stiffening. So we recommend preventing further environmental deterioration at the critical sections and reducing pendentive demand as soon as possible to stabilize the damage. We'd like to acknowledge the funding sources, the Getty Foundation and Princeton University, as well as the project partners listed here. You may contact me with further questions and visit Keeping ESA Modern for further project information. Thank you.